Patterson here. Today we're going to go over tonicity and we're going to work some water potential problems. This is AP Biology Unit 2. So let's review real quick. Remember we talked about different types of solutions. I have hypertonic, isotonic, and hypotonic, and how the number of solutes inside or outside the cell can change how the fluid or the solution moves. So let's look at isotonic. Here I have equal concentrations. My material is going to flow back and forth at the same rate. So what this is saying is that my concentration outside is similar to my concentration inside. So one water molecule is going to come in, one molecule is going to leave. So this is going to be a back and forth movement of material. And if you need to review, I'll put that down in the comments and in the description. The video you guys can watch where I go more in depth into this. I have hypertonic. This is going to be the solute concentration is higher outside the cell. So remember, hyper is very active, okay? And you can think of a solution that's hyper is going to have a lot of solutes in it. And so with it has more solutes in it, it means it has less water. So when we talk about tonicity, we're talking about water. These are osmosis problems. And we want to know, where's the water going to go? If I have a solution that has a high amount of solutes, that means I have less water. So water wants to go, again, from a high concentration to a lower concentration. So water is going to go where I have higher solutes because I'll have less water there. So remember, we said that water follows the solute. So with it following the solutes, it's going to leave the area where there's lower to go to higher. The water will diffuse out and I'll have plasmolysis. Plants and animal cells do not like a hypertonic environment. Hypotonic is when the solute concentration is lower outside the cell. So if my solute concentration is lower, that means I have more water molecules out there. I have less solutes taking up space, and I have more water molecules outside in that solution. So that means inside I have more solutes. So if I have more solutes, that means I have less water. I have a lower concentration of water. So water wants to go from a high concentration to a low concentration, so it's going to rush in. Animal cells don't like that. They will lyse and they will burst. Plant cells love it. They'll do this turgid pressure with that type of hypotonic environment. And if you remember, we said like hypo, hippo, big and round. Also, this O is big and round, and that kind of lets you know that this is going to get really, really big. Hypertonic, see how that E kind of folds in on itself? And that's kind of what happens when the cell shrivels up. So you can see either one of those and you kind of know what's going on. But hypo, my solute concentration is lower outside of the cell or in my environment that I'm in. So let's talk about water potential. Water potential predicts the direction water is going to flow based on the solute concentration and the pressure. So here I have pure water, which means I have no solutes in it. Inside the cell, I have solutes. So these solutes are taking up space that water could take. So that means I have less water concentration inside and more concentration outside. So water is naturally going to want to go into the cell because I have less percentage of water. We say that the cell is in a hypotonic environment because I have less solutes out here than what is in here. So water will rush in, cause this to swell, and if it's an animal cell, it will lyse. Here I have the opposite. I have more solute outside. I have a higher concentration of solutes outside than I do inside. So that means these solutes are taking up places where water could be. So I have a lower concentration of water molecules out here, and I have a higher concentration of water molecules in here. So it wants to go from a high to a low environment. So these are going to leave the cell. This will shrivel up as the water leaves it to go into the solution. So we say the cell is in a hypertonic environment, and the hypertonic environment means I have more solute outside. So the potato cell has a lower water potential than the surrounding environment. So this is going to be a lower water potential, which means that the potato cell has more solute inside and less water. Then we do the other one. We go back and look at this one. The potato cell has a higher water potential than their surrounding environment, which means that the potato cell has less solute and more water to move. So when we say a higher water potential, it means that it's going to move water out. So water likes to flow from areas of a low solute concentration to areas of a high solute concentration. Notice solutes, okay? So if I have a low solute concentration, it means I have more water. If I have a high solute concentration, it means I have less water. Water wants to go from a high water concentration to a low water concentration. So it's going to go from a low solute concentration to a high, because that means I have less water here. So here I have my water, I have no solutes out here, and so we said that the water is going to want to go inside, okay? And then here it wants to go out. I have a high solute concentration out here, so the water is going to want to leave the cell. We also say high water potential to areas of low water potential. So again, I have a high water potential to a low water potential. I have a high water potential to a low water potential. I go from a high pressure to a low pressure. So I can go from an area where I have a lot of force being pushed on to an area where I have less force being pushed. So when this happens, water comes in, I'm going to swell, water leaves, the cell will shrink and shrivel. So here's my water potential formula. This is water potential. This is the Greek letter for psi, but we'll just say some type of potential. If it doesn't have a letter next to it, this is water. Sometimes you'll see a W, and that means water potential. It will be measured in megapascals or bars. 1 megapascal equals 10 bars. Most of the time, it will just stay bars. That's kind of what AP Bio I've seen more of, is the bars versus megapascals. But I would still know it both ways. Here I have solute potential. This is telling you your osmotic potential, how my water is going to move, how I predict the direction water is going to go. The more solutes in a solution, the more they're going to bind to the water. They're going to start taking up space of the water. They're going to reduce the water potential, and that number is going to be expressed as a negative value. Pure water is going to be 0 megapascals because, again, I have no solutes in there, and so I have no solute potential because there are no solutes in my solution. So distilled water would be 0 megapascals. This is my pressure potential. This is the physical pressure on a solution. You can have atmospheric pressure kind of on that too. It can be in a positive or negative to the atmospheric pressure. And if it says open air, the pressure is going to be 0 megapascals. Sometimes you might have like a piston or something where it will talk about a pressure. And so that's what it's going to be. If it's just open air, or if they don't mention it, it's 0 megapascals. The solute potential of a solution. Here I have my potential, and this S means solutes. Okay, so my solute solution. And then this is my formula for that. So this will still be measured in megapascals or bars. And then now I have this other part here that I have to break down. So I have this negative I. That's my ionization constant. And that usually pertains to two types of molecules. I have sucrose, which will be considered a 1. You'll just put a 1 in for if it's sucrose. If it's sodium chloride, then it's going to be a 2. And what this means is that, does it disassociate in water? Sugar does not disassociate in water, so it stays one molecule. Salt disassociates in water and becomes a sodium ion and a chlorine ion, and so these will break down into two different parts. So your number will be a 1 or a 2 depending on which one you're looking at. This is my molar concentration. This is how many moles of a solute is in a solution. That is my pressure constant. There's two types. The one that most AP Bio tests do is this one, but you might have to use this one if they give it to you. But for the most part, it's this one that you're going to use on your test. Next, you have the temperature. The temperature is going to be in kelvins. So you have to go from 273 plus your degrees Celsius. And if you do that, that gives it to you in kelvins. So let's look at some practice problems. Okay, we've got about 10 of them, and so let's work some of these together. If you are coming through this again, I would recommend come back later, go through it again, and then rework them, pause it, rework it, but I'm just going to go through them, and we're just going to work through these one by one. So let's look at first one. If a plant cell has a lower water potential than its surrounding environment, and if pressure potential is equal to 0, is the cell hypertonic or hypotonic to its environment? Will the cell gain or lose water? So let's look at this. I highlighted this. It has a lower water potential. So if a plant cell has a lower water potential, that means what? That means I have solutes in here. And if I have solutes in here, that is telling me that these solutes are taking up space of water. So this is going to have a lower concentration of water than the outside. My pressure is 0, so that's just, I don't really have to worry about that right now. So what's going to happen? Where is my water going to go? Where do I have more concentration of water to less? Because I'm going to go from more concentration of water to a lower concentration of water. So I'm going to go and I look at my cell. So let's just play with some numbers. I'm just going to show you some numbers right here. So let's say my cell was negative 2.5 bars, and this is telling me my water potential. This will tell me like my solute concentration. My solution has negative 1.5 bars. So you can see here that I have more solute, I have more potential right here. So what this is saying is that the cell, I like to think of it as this has more solute. So if this has more solute, then that means I have less water. This has less solute, so this means it has more water. So my water is going to want to go into the cell. So this has more solute, so I have less water, so the water is going to go into the cell. So is it going to gain or lose? It's going to gain. The cell is going to be hypertonic to its environment, because remember, I have more solutes than the other one, then it's going to be hypertonic. So this is hypertonic to its environment. Water is going to go from an area of high potential, which is the environment, to an area of low water potential, which is in the cell. I had less water inside the cell, so it's a low water potential. All right, practice 2. What is the solute potential of a 1 mole sucrose solution at 22 degrees Celsius under standard atmospheric conditions? So let's look at what we need to solve for. I need to solve for the solute potential. So I have to ask, do I have a formula for that? Yes, I do. So here I have my solute potential, and then I have this formula right here. So let's start breaking down all these pieces and see what that looks like here. So let's look at I. What solution am I working with? I'm working with sucrose. And if you remember, we looked at sucrose. Okay, 1 is for sucrose, 2 is for salt. So I'm going to have 1 for sucrose. I look at C, this is my moles. A capital M is a mole, so that is going to be 1.0 moles. I look at R. R right here is my pressure constant, so this is the number that I will always use for R. This is going to be a constant number. Then I have temperature. This is going to be 22 degrees Celsius, but remember, I just can't use this. I have to add 273. So I'm going to take 22 plus 273, add those together, and that's going to give me 295 kelvins. So now I plug everything in. So I have 1, 1, my constant, and then I have my temperature here, and then I'm going to multiply those together. And remember, it's all negative, so I'm going to have a negative number, which is negative 24.5 bars. Okay, let's look at practice number 3. I have the zucchini cores are measured and determined to have a sucrose concentration of 0.36 moles. Calculate the solute potential, the psi S, of these cells at 22 degrees Celsius. So let's look, what formula do I need? I need to solve for that. So do I have a formula for that? Yes, I do. So now what I'm going to do is start looking through this and see what I've got. So I'm going to come through and I have a sucrose concentration, all right? So that's telling me what number am I going to use for I. Should be 1. Now I'm going to look at the next thing I come to, which is this one right here. So what is this? What does this represent? C. That's my moles. So my molar concentration is C. So now I have to look, what do I have next? I have this right here, temperature. And remember, I can't just do this. I have to go in and do 22 plus 273. And that's going to give me this number here in kelvins. And what I'll do is I write this number next to it so I don't have to keep going back to figuring out this part right here. I'll write it on my paper and maybe circle it or just put it next to this so I know what that is. All right, so now I have C, and I have T, but I need to find R. I don't have R here. Do you remember where R is at? Right there. So I'm going to go in and I need to write down my constant. So my constant will be this number right here. So I do 1 sucrose, I do my moles, I do my constant, and then I take this and I put this in. I multiply those together and I get negative 8.83 bars. So now, if the zucchini cores are placed in pure water, will water go into or out of the plant cell? So explain. So remember, my zucchini core that I figured out was negative 8.83 bars. If I put this zucchini into this water, okay, I have it in pure water, what's going to happen? So now you need to ask, where do I have more solute? Because where I have more solute means I have less water. So I have more solute inside the cell, so that means I have less water. So what's going to happen? Which way is my water going to want to go? So my pure water is 0 bars. So this means I have more solute. I have less solute. So water wants to go where I have a higher concentration of solute. So it's going to want to go into the cell. So that means it's going to expand, it's going to swell. If it's a plant cell, turgid pressure. If it is an animal cell, cytolysis, it's going to lyse. Okay. So we're just following the solutes. Water will go into the plant cell because it has a lower water potential, than the surrounding environment. Okay, because I have a lower amount of water here than I do outside. All right, number 4. A dialysis bag contains 0.1% sucrose and is placed in a beaker containing 0.4 sucrose. The beaker is open to the atmosphere, so that means 0 pressure. Okay, assume that the pressure is 0 in an open beaker. So here I have my initial value of my beaker contents, 0.4 sucrose solution. My solute potential is a negative 4. So they're already telling you they've already solved for it. So this is a negative 4 bars solution. I have my dialysis bag. My solute potential is negative 1. So this bag is a negative 1 bars solute potential. Okay. So now what's going to happen? So what is the water potential of the beaker? It's going to be negative 4. Water potential of the bag is negative 1. So where do I have more solute? Wherever I have more solute means I have less water. Water wants to follow the solutes, so it wants to go where I have more. So water is going to move out of the dialysis bag. Okay, I have more sugar out here, more sucrose out here, so that means I have less water, so it wants to go out of the bag. Number 5, if a potato is allowed to dehydrate, so that means its water is going to evaporate out. If a potato is allowed to dehydrate by sitting in the open air, would the water potential of the potato cells decrease or increase? So the water potential of the potato. So if my water is leaving, that means I'm going to have a lot more solutes inside, right? I'm going to start building up a higher and higher concentration of solutes because my water is leaving. So what does that mean? That means that water is going to leave, my cell is going to shrink, my solute concentration is going to increase. So the water potential will decrease in the cell because the water has left. The solute concentration inside the cell is going to increase, decreasing the solute potential. So my solute potential is going to go down. The solute potential inside will become more negative because, again, remember, the more negative that number is, the more solutes that are there. So when we look at these bars, if I have -5 and -2, -5 means I have less water and a lot more solutes in it. So the more negative it becomes, the more concentrated my solute is inside. Let's look at number 6. What is the water potential for sucrose solution that is at 0.1 molars at a temperature of 10 degrees Celsius? So let's look. What do I need to solve for? I need to solve for water potential. So I have a formula for that. So it's this right here. Okay, I have my solute potential and my pressure potential. So I need to look right here. The water potential will be equal to the solute potential of a solution in an open container because the pressure potential of the solution in an open container is 0. So what it's saying, if I'm in an open container, my water potential will be the same as my solute potential. When pressure is added, then these two can be different. But if this is 0, these are always going to be the same number. So let's solve for my solute potential, because if I solve for this, I'm getting the same number as that. So I need to find my I, my C, my R, and my T. So I'm going to look. I come to my first one, which is sucrose. What number is sucrose for I? It's 1. I look again, and I get to this one right here. This is going to be my mole concentration, my molars. So this is going to be 0.1, it's going to be C. I look, I have temperature, so I take temperature, I add 273, that is my temperature in kelvins. I write that by my degrees Celsius. Remember, I need R. R is right here. So I'm going to write that number down too. So I multiply all 4 of those together, and you're going to get negative 2.35 bars. My water potential will also be negative 2.35 bars because I'm in an open container. Okay, number 7. What is the solute potential for salt solution at 0.5 molars at 25 degrees Celsius? So what do I need to solve for? I need to solve for solute potential. Do I have a formula for that? Yes. So I'm going to take this and I need to find my pieces here. So I look, the first thing I come to is salt. That is my ionization. What number was salt? It was a 2. So remember, we have a 2 for salt. Sucrose was 1, salt is 2. So I found my I. Next, I have this. What is this? That is my C. So now I found my C. I have this, which is my temperature. I take that, add 273. I write that over here. My R is going to be right here. So now I have everything I need to solve. So I have 2, I have C, I have R, and I have T. So my answer is going to be negative 24.8 bars. And that will be my solute potential. Now, if it was in an open container and no pressure being added, this would also be my water potential. All right, a plant cell has a solute potential of negative 4 bars and a pressure potential of 1 bar. What is its water potential? So I have to solve for water potential. This time I have a solute potential, which is this, and now they're telling me pressure. So now I have something a little bit more. Water, these two do not equal the same right now because I have pressure being added. So let's look at this. I have my solute potential, I have my pressure potential, and I just add those two together. So I add those together and I'll have negative 3 bars would be my water potential for this plant cell. So if this cell is placed in a solution with a water potential of negative 5 bars, what's going to happen to this cell? So remember, I've already figured out this plant cell is negative 3 bars. That is my water potential. My water potential of this solution is negative 5. Take a second and think about what is going to happen. Is water going to want to leave the cell, or is water wanting to go into the cell? Where do I have more solute? All right, so wherever I have more solute means I have less water. So the solution has a lower water potential, and the water is going to flow out of the cell into the solution. I have more solute, so I have less water. I have less solute, I have more water. So it's going to flow out of the cell. My cell is going to start to plasmolyze, and the cell membrane is going to start to pull in on itself as the water leaves. All right, number 9. The value for water potential in root tissue was found to be negative 3.3 bars. If you take the root tissue and place it in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the water potential of the solution? And in which direction will the net flow of water be? So we got to ask, what am I looking for? What do I need to solve for? Right now, they're giving me this. They told me the value for my water potential in a root was negative 3.3 bars. So they're already telling me this. They're giving me this answer. So now I have to figure out the solution. What is the water potential of the solution? So I need to think, all right, remember, if this is an open container, my water solution and my water solute is going to be the same. So this here is my potential for the root. This is going to be my potential for the solution. But these are both psi S, my potential of my solute for both of these. Okay, I am going to use this formula. So let's look at what we got. I have 0.1 moles. So that's going to be C. I go through. I have sucrose. Sucrose, remember, is a 1. So I will have 1 right here. I have 20 degrees Celsius. That's my temp. So I add that to 273 and I get my kelvins. So I'm going to put that over here. My R is going to be right there. I multiply those 4 together and I get negative 2.4 bars. So now the question is, in which direction would the net flow of water be? Where do I have more solute? Where do I have less water? I have more solute here. I have less solute here. So what's going to happen is water is going to go into the root because I have more solute. All right, number 10. You are stranded in a lifeboat with several other people in the middle of the ocean. You have run out of clean drinking water and are very thirsty. The others have started to drink seawater to quench their thirst. Since you are waiting for rescue, you decide to solve a couple of water potential problems to determine if drinking seawater is a good idea or not. Spoiler alert, it's not. All right, so let's look at A. The majority of dissolved ions in seawater is NaCl. Roughly 0.5 molars of the salt concentration. The ionization constant of salt is 2. We know that already. Calculate the solute potential for seawater if you know that water is 2 degrees Celsius. So what am I solving for? Solute potential. I have a formula for that. Is this one right here. Okay. So now I'm going to find all the stuff that I have. So I know 0.5. I have 2 as my salt. I have my temperature. I'm going to add those together. And then my constant, which is this right here. I go through, I multiply all 4 of those together, and I'm going to be negative 22.9 bars. So this is the seawater. And if I wanted to, I could say seawater here if I wanted to instead of solution, but this is talking about the solutes. All right, your own cells have 0.15 molars of salt. Calculate the solute potential for your own cells knowing that your body temperature is 37 degrees Celsius. So now I'm going to put this down here. This is the salt water. And now I need to find it for the cell. So I'm going to go through and plug in my pieces. So I have C, I have I, which is 2, remember. I have temperature, I'll take that, add 273. I have my constant, which is this right here. I multiply those 4 together, and I get negative 7.7 bars. So using your knowledge about water potential, if you drink the seawater, what will happen when the seawater comes in contact with your body cells? So let's look. My solution was negative 22.9 bars. My cells are negative 7.7 bars. Which one has more solutes? The seawater has more solutes. So what's going to happen to my water? What direction is water going to go? Water follows the solutes. So I have more solutes here. Water is going to go in this direction. So water is going to flow out of the cell and go into the solution, the seawater. So is drinking seawater a good idea for survival? What effect will drinking seawater have on you and your chances of surviving until you're rescued? No, seawater has a very low water potential because it has a high concentration of salt. Your cells are going to lose water and you will become dehydrated, and that is not good for survival. So understanding these concepts really kind of help you understand what's going on inside your body and what happens when you are dehydrated. All right, that was it for this. I would go back, rework these problems, separate piece of paper, and just kind of get in it. You've got to get into the habit of just practicing these problems. Once you kind of get it, it's going to click and you're going to be fine. But just start following the solutes and water will go wherever I have more solutes. I hope that was helpful. If it was, let me know. We'll talk to you later. Bye.